Hello friends, welcome you all to the 12th session of the ARM based development class. Today we will be covering a few more instructions after having touched upon data processing and data transfer instructions. So the following are the kind of instructions that we will be looking at today. There is one special instruction called swap. I will explain you what it is and where is it used for, and what are the precautions that we need to take while using them. And then there are set of instructions which are reserved only to operate on the processor status registers, and then some pseudo instructions. I will tell you what exactly they are. Okay. Swap instruction. So all of you are aware what do we mean by swap, right? So suppose you have one content in a particular place. Okay. Assume this is a register or memory. It is having two values A and B. Okay, just a read and write will try to read from the content from here, and then write means it will write new content overwriting the existing value. When you do swap, what happens is we are interchanging the values in these locations. Okay, so A will go here and B will come there. So in our case, in the processor case, CPU is here, the processor, okay, ARM processor is there, and we have a memory. Okay, now we want to swap contents between these two. That means what? We have some register, a specific register in the processor, and then some specific location in the memory. Then we want to swap the contents. Now it is very logical to say when you are swapping the contents, the number of bits that we transfer or the number of bits that we swap should be the same, right? Suppose if you are swapping 32-bit value, means this 32-bit value comes here and this 32 value will go here. Similarly, we could also do a 8-bit. If you are swapping two 8-bit values, some 8-bit low LSB of this and LSB of this will get transferred. So basically, a swap means interchanging two values between two locations. In our case, it is between a register and a memory location. Now we may wonder why do we need one special instruction for this? We could do this way, right? I will say that okay, suppose I want to transfer a register value which is in R0 to a memory location, our favorite address 1000. What we can do? We can do it through two instructions. First we say that move R0 to this location. Okay. Now what happens? This content is overwritten. If you transfer it straight away, you are not preserving this value, correct? So what we should do first? We should read this content. Okay. Suppose you are interested in transferring the swapping the content between 1000. You should read whatever is stored here to some temporary register. Okay. Let us call it as R1, another register I am using, and then I am interested in swapping between R0 I said initially. So I will write R0 into that location. Okay. So what happens? Now we are overwriting this content with the value in R0, but we have preserved what was the old content at that location, and then we can internally move R0 from R1. We can move the content. Okay, because it has already come into the register processor. Okay, so we are doing two memory operations. One is read, memory read, okay, and then one is memory write, and then one register transfer to accomplish this job. We could do this, but swap is not introduced in the processor to save all these three different instructions into one. The main purpose is not that. The main purpose is when I am doing this exchange, I want to make sure that the content that I am interested in swapping with, I don't want any other processor or any other memory operation to change that value in between. You may wonder how can it happen? Anyway, I am doing it immediately after one instruction each. So why should it or how should it happen? In a typical example here, even if I am doing it with 3 consecutive register instructions, please remember once one instruction is executed in a processor, interrupt can happen. Okay. So after completing the instruction execution, the processor looks at whether any interrupts are there or any exceptions are there. It will go and then perform, go to the handler and do the job, whatever is meant in the handler, mentioned in the handler, and then comes back and execute the next instruction. So there can be a interruption between 2 instructions. Okay, you cannot make sure that 2 instructions are executed one after the other. There is no guarantee. That is one point. Another one is this processor may be running it continuously without any interruption, but imagine a case where there is a common bus. There are processor here T1. It's a multiprocessor system. Okay, there is another processor T2, which is also connected to the same same bus. This is bus. Okay, sorry about the lines. It is like Indian roads. Okay, this is a memory. This is common memory, which is being accessed by both the processors. Now what happens? The bus normally, if you are aware of all the bus interactions, there will be an arbiter in the bus, okay, which will be allocating the memory cycles for each processor. Okay. So suppose I am executing this whole instruction in this P1, it has executed the first instruction of reading from 1000. After that, the bus is given to P2, because every memory cycle can be broken into multiple things, and then the arbiter can come into play and then give the access to any kind of processor. Now you assume an worst case scenario where P2 is also updating the same location that you are interested in updating in P1. Where it is shared memory. So what happens? What you read between somebody has changed it. Okay, we do not want this particular scenario to happen. I will explain you why it is important not to have any other processor or any interruption to modify the value before this swapping happens. So to make sure that this swapping operation is done without any interruption between the memory cycles, we are using a swap instruction. Okay. So how does it make? Because swap instruction is executed in one particular processor. Okay, you are executing the swap instruction in this processor. It doesn't have any control on what happens with this processor, but the P1, the processor which is executing the swap instruction, make sure that it informs the memory controller. Okay, with a log signal. There is assume there is one more signal going apart from data, address, and read, write, all those things, to indicate to the memory, hey, I am doing a swap operation which will involve one read and write. So I do not want any other memory cycle stealing happening in between these transactions. So what happens is indirectly the memory prevents from other processors in the same bus accessing the same memory, okay, getting a control before this transaction happens. With this particular scenario, with the support of hardware, with the support of the memory, okay, this swap instruction works. So it is not that only the processor decides, but only based on the swap instruction, it knows that okay, it is supposed to generate a lock signal to the memory to say that this transaction involves one read, okay, one read here and then one write here, which should not be broken in between. That means it should not be interrupted with some other memory read or write from any other processor or a DMA. See, DMA could have been programmed by some other processor to transfer some content, maybe from a peripheral to the memory. Okay, it may do a read write, so that may also access the same particular location, the 1000 that processor is interested in accessing. So it could be a DMA or it could be a different processor, or the same processor may have an ISR or handler which may modify the value. So we don't want this particular value to be touched by anybody else before the swap operation completes the operation. Okay, so I hope this is clear to you. why we need it. Let us see. Okay, I'll tell you some more examples so that this is the background of this. Once I explain you this, you will be clear about that. Okay. Now, what is the format of swap instruction? I told you swap could be a word transfer exchange, word exchange, or a byte exchange. Okay. So B could be written before swap in front of swap, so that to indicate that it is a byte exchange. Condition code, you are all aware. If there is a condition code mentioned, if it satisfies only, this instruction will be executed. And RD, RM, and R. What are they? RN, from the symbol you can make out that this is a base register. Okay. The value pointed to by RN is the location where you are interested in exchanging the information. Okay. In our case, RN may be having 1000. So in that case, we will be exchanging the value which is there at the location 1000 with the registers. Now, what are these registers? There are two things mentioned here. What it means is, I can, what you can see the what is happening. See, whatever is pointed to by RN is a memory 32-bit operation. If it is a swap, if it is a swap byte, it's a memory 8. Okay. So that address, whatever is the content, is swapped to a temporary location because it cannot overwrite on the destination register directly, because I might have both RD and RM mentioned as the same register. Now, for a moment, assume that I have mentioned this as R1, okay, this as R2. What does it mean? I am interested in writing the value which is in R2 into the base register, whichever it is pointing at. That value I want to transfer it, and then what RN was having earlier, I am interested in writing into R1. So this is alright if these two registers are different, but suppose if I have mentioned both registers same, I can do that also. This instruction allows it. Okay, because main purpose I mentioned that I am interested in exchanging information between a register and a memory. So though this instruction provides two operands here to be mentioned as two different register values, you could also decide to do it with one. In the case, what happens? The value which is being read from RN should be kept somewhere temporarily for us to write the value which was there in the R1 to the memory, and then whatever you read from the memory you copy into R1. So that is why you see that there is a temporary location coming here. What is this temporary location? Is it a memory or a register? It is a register which is inside the processor. We don't know how. It could be a buffer which is maintained by the processor. Okay, it copies the value which has been read from the memory. Temporarily it keeps it here. Okay, and then you have written, you said that I am interested in changing the R1 value, so it goes back to the same location in the memory. Okay, so this is the memory, and then what happens? This temporary location, whatever value was read from the memory, goes here. So finally what happens? These two values are being exchanged. That is what we are doing using this instruction. So we could do either a byte or a word transfer. Good. Let us see. Now, it's a special case of load store. Okay, because it involves one load as well as one store. First, what happens? First load happens and then store happens. It starts the contents of memory with the contents of a register. I explained you already. So what do we call this operation as? It's an atomic operation. Why do we say it's atomic? Because the read and write happen in the same memory cycle. What I mean by same memory cycle means, though read cycle happens and write cycle happens, there is no other memory cycle in between them. It is not broken. So the preventing any other instruction from reading or writing this location in between. Okay. So swap cannot be interrupted by any other instruction or any other bus activities. Very important. It can't be interrupted by any other instruction or any other bus activities. So what I mean by any other instruction means, the swap instruction gets completed only when both read and write are done. So even if an ISR, external interrupt happens or exception happens, it will wait for this particular instruction to be executed fully. before it can be interrupted. Similarly, the bus also cannot give the control to the some other processor or a DMA before this particular swap instruction gets executed. Okay, this is what is called hold the bus. Okay, the swap instruction holds the bus until the transaction is complete. Okay, now I told that it cannot be interrupted and it has to be done in a single cycle, all that, but I have not told you why it is required. Okay, I will tell you for a moment. Please hold on. Then let us look at the format, and then I will take you to the place where I will explain you why it is required and where it is needed. Okay. Let us see the instruction format. This is very important, as we have seen so many formats so far. Now you see here you could see that the opcode or the special bit pattern after the conditional flag in this indicator 4-bit value, it is increasing. If you remember, the data processing had only 00 and the data transfer had 01, if I remember correctly. But now it is a 5-bit value. Why? Because they have to somehow encode them into the available 32-bit value. And one advantage of relaxed number of bits allotted for this is there are no other address formats supported by this instruction. If you remember, we had a whole lot of 12-bit reserved for the immediate constant, and then we tried, we did so many kinds of shift and rotate operations on it before the operand was given to the RD or it was used by the instruction. In this case, you see only the registered values are mentioned. Okay, so it is clearly, you can make out that you cannot do any shift operation or any other rotate operation on the operand 2. Even if it is there one operand which can go through barrel shifter, you cannot mention any of those operations in this swap instruction. Okay, so effectively this is the format. Okay, these are all reserved. Okay, some values. Now I think everything is clear to you from the explanation. So Rn is the base register which is getting swapped with the value in. Okay, Rm gets written into, and the Rm value is written into the. Okay, let me write it again for you to recall. So Rm is written into Rn, and what was there in Rn goes into Rd. Okay, and as I mentioned, these two can be same registers also. So there are two locations maintained in the instruction format, but it can hold the same value. It can have 1, and this also can be mentioned as 1. Okay, I'm sorry, these two. Okay, Rd and Rm only can be sent, but Rn has to be different. Okay, the base register and these two, all you cannot mention everything as same. Okay, only Rd and Rm can be same, but Rn needs to be a different register. Okay, if it is 1, it could be 2 or whatever remaining values. Very good. So no offset completion options are available in this, as I mentioned to you. Okay, let us see where is it used. I explained this already. Multiple processors. Okay, this processors I mentioned, DMA I mentioned, but within the processor itself, all of you must be aware, within the processor itself there can be multiple processors running. Okay, P1, P2, they are different processors. Okay, now if you have a basic OS understanding, any process, okay, can be swapped. Okay, what I mean by swapped is this particular process which is running in this processor is swapped out to the memory. Okay, all the contents of all the registers are copied, and then a new process is brought into the CPU. So what happens? Another process starts running. So the context switch, that is what we call as a context switch, and one process may be doing that operation whatever I mentioned, and in between it could be interrupted because the time slice may happen. If you recall in your OS course, time slices are there between two time slices processes. The OS scheduler decides to come and then remove this process which has already executed so much time in their processor. It swaps it out and then brings another process. So this switching, context switching could happen between those three instructions I mentioned to you. So because I mentioned that the memory whatever is being accessed cannot be interrupted, even this should not happen. Okay. So by performing a swap operation which is atomic, we can avoid all three of them. Okay. Very good. Now let us see. I mentioned to you RD and RM may be same register. Okay. And memory values are exchanged between the register and the memory. But RN should be distinct from these two. I told you that also. One more important point is PC. The R15 cannot be used as any of these operands. Okay. You cannot mention R5 at all, R15 at all in the swap instruction, because it is a pointer to the program, so it doesn't make sense to change that content at all, right? Because when you are using R15, what are you trying to do? Suppose you are using here, you are trying to modify the content of the program itself, because the PC will be pointing at the program code. So you cannot go and swap with some other content of RN or RM, and then it may have unpredictable results. So ARM processor doesn't allow such kind of a transfer. And ARM executes separate memory read and write cycles. Okay, they perform one read cycle and one write cycle, but in between I mentioned to you a log signal is generated to indicate to the memory that once the read has happened, do not break the memory cycle, allow another write cycle to happen from the same processor, so that both of them happen simultaneously without any break in between. Okay. Very good. Now let us see. I am giving you an example first and then telling you where it is useful. I hope most of you would have heard semaphore in your previous course in the operating system course, but just to refresh your memory, I will tell you where exactly it is used and how it is implemented in a particular processor. It could be done in a different way, but I am taking one sample and then telling you how it is done. Take an example. Suppose this is the data. Okay, it's a very critical database. Database means it could be a one single word also, or it could be a structure also, which is in the memory. Okay, this is in memory. Now this is the CPU. Okay, I am drawing a very big CPU here. Here CPU is the processor with the two processes running, P1 and P2. Okay. Now both of them are accessing this database. Okay, reading and modifying something, but we don't want both the processes to be in the database. When I say in the database means when they are accessing them, I call that they are in the database, that they are in the middle of doing something. We do not want both the processes to be given access to this. Okay, while other process is doing something with the database, because there will be a inconsistency. It is similar to allowing you to log in to your bank account from two web browsers. Okay, if you have tried to use your Citibank or any bank, HDFC or any bank, you are trying to access your account, FD account. Suppose you open a browser. Okay, you are accessing it with the same user ID password, and then maybe you have a mobile or another tablet, or maybe on the same PC with another login. You are trying to use the same account. You are trying to access your account. What does it happen normally? It says that it is already open or your account is already being used, so it doesn't allow you to access it from two places, right? So it is similar to this. That means it doesn't allow two people working on the same database at the same time. So this could happen in a railway reservation or anything. Suppose two people are trying to reserve a particular seat in a railway, particular train. We don't want two people to access the same seat to be allotted to two people. We don't want the same berth allotted to two people. So it locks two processes from accessing the same location, so that it doesn't happen. How is it done in a typical OS environment? Semaphore is used. So when a particular database is there, suppose assume that this is a DB1. I will call one semaphore. I will as a programmer, as a application programmer of this particular database success, I will say S1 is a data semaphore which is to be acquired before any process does anything with the database. So this is a discipline that I am insisting on for the processors to adhere to, so that they don't do any changes to the database simultaneously. So it is a kind of a lock, okay, entry lock. It is like key is given only to one person at a time. So S1 is some entity, it's a database, okay. It's another data variable which is OS specific, and database is your own data, and then you are trying to tell any process using this should first acquire something. What I mean by acquiring, I can say that whenever a process comes and access this S1, okay, this is a semaphore, it will look for whether it is free or not, whether is it free. What I mean by free, if suppose this has a variable inside that, and then if it is 1, I call it is free. Then what I do, when this process reads this value and it finds that it is 1, it will write back 0 into it to say that it is no longer free, okay. Now assume P1 has come first, and then it was seeing that the semaphore is 1, so it has taken the semaphore. That means it has taken the value which was there in it, copied into its own local register somewhere, and then it has written 0 into it. Now what happens? P2 comes, it will ask for the semaphore, and then it is 0 now, so it will be blocked. This process will not continue with the execution, it will be blocked waiting for the semaphore to be filled. Now what happens? P1 comes in, it does some operation with the database, and then it has to remember to come and release it again, okay. That means what? It will write back 1 and then make sure that it is released. Then the waiting process will come back and get the semaphore and then go into the database. So this is the set of operations to be performed for acquiring a semaphore. So how do we implement it in a processor? So processor need to support it. Why? Because when a particular process is reading the value, semaphore value, it may see that it is 1, and then it may think that okay, it is free, and then it will say that okay, I want to write back 0. But by the time if the processor is interrupted or a memory is access is given to some other processor or a process, what will happen is that will also read this value as 1, and then it will think that okay, it is semaphore is available, and it will also write the 0. So what happens? Now two processors assume that the semaphore is free, and then they get confused, or there will be a confusion or a chaos in the while they enter the database, okay. So to prevent it, this swap instruction is done so that when any process sees that it is 1, it immediately makes sure that it is written with a 0 value before anyone can access it to find out that it had 1. So if that is prevented, then this kind of a confusion will never happen, right. So that is what is achieved by using this instruction, because it needs some help from the memory also as well as from the processor. So this is what is done with a swap instruction, okay. So assume that this is a precondition, 1000 is the address, and then R1 is having a 00 value. Now initially it is exchanged. R0 is having what happened? 1000 is at 1000, 1 is having 1 is stored. So when this swap instruction is executed, R1 becomes 1 because that 1 has come to these two have been swapped, okay. 0 has come here and 1 has come there. Now this is acquiring a semaphore, and releasing a semaphore is doing the reverse of that, okay. Again you do the same thing. What happens is if they get exchanged, and then the reverse of whatever happened is so 1 comes back to this memory, and then 0 is gone back to 0 R1. So this is what is the use of this swap instruction, okay. So this is what I am explaining. Semaphore is acquired by swapping the value, and then memory is made 0, and the value which was there inside was stored into the register, and then it is released back by setting it 1, okay. So the critical region, what I call is, it could be a part of a code or it could be a part of memory which only one process can access at a time. Okay. So I hope swap is understood and the semaphore and where it is used is understood. Okay. So let us go into next one. One small quiz. Okay. Take a small break, read through this, and then find out which one of the options are correct. Only one option is correct. Please choose the one. Okay. Welcome back. So all of you might have thought over it. Let us see what is the correct option. So option B is the correct one. So as I explained to you, it is not a single load or store happens. It is a multiple load and not multiple load. One load and one store happens. So the number of cycles spent on load and store will be there in this instruction also. Only thing is they are happening together. So it will take more cycles than a single load store. Because single load is only a one load operation or a single load store operation. But here we do both load and store. So it will be 2 cycles involved in this. So let us see now what is the timing involved in this. Okay. This you are all already familiar with this. So I will little bit rush to it. So you know that this is only a sequential access because our instruction getting accessed. Here there is a what happens, the value which is in Rn base register is loaded into the address register for a memory cycle to start. So that takes an internal cycle here, but at the same time an instruction also getting fetched. So it is BIS instruction. So this is the place where the swap is getting executed. So initially I told you read happens. Okay. How many cycles it will take? Is it non-sequential, sequential? By now you should be very clear. It is non-sequential. And then what happens here? Here RM is getting written into data out register, and a write cycle happens here. Okay. So though it is the same address, one is read and one is write. So memory takes the same non-sequential cycle time, and then once the value is written out, the value which was in data in after this memory read gets copied into RD, because it assumes that RD RM could be the same register. So it delays overwriting the value. I mentioned the temporary register, if you recall, that is nothing but data in register. It could be okay. So the value which comes in sits in data in. It doesn't go to the register directly until this data write happens. After that, it is copied into RD. So this is something to do with the internal operation. The internal cycle happens. So total time taken will be one sequential cycle and two non-sequential cycles and one internal cycle. This is what a swap instruction takes. Okay. So if it happens to be same register also, the same thing happens. The data in register holds the value in between before the transfer happens. So this is what you will be writing in case if it is a same register. Okay. I hope you understand this very pretty well. Let us go into another concept, which is something to do with the status register related operations. So by now all of you are aware what I mean by status register is nothing but our CPSR. Okay. So why is it treated separately? If you recall, status register is something different from the internal data general purpose register, because it is meant for maintaining conditional codes and more processor mode and then interrupt flags and all those things, right? So to perform any operation with that, that means to transfer that content to any other memory location or something, you need to first bring that status register into a register, a general purpose register, and then transfer it to memory. So these instructions are meant for that operation. So how do I differentiate MRS with MSR? It is very simple. It is like ARM processor typical convention. Okay, move, M is move. Okay, M is nothing but move. R equal to S. That means status register is moved into register if you use MRS. Okay, MSR is the reverse of that. What happens? A register, the status register is the general purpose register is moved into status register. Okay. So here R and S means what? This is CPSR. or SPSR. Okay, you know what they are. This is current processor register and this is a saved processor status register. This happens in a privileged mode and this is in a user mode, right? And R means any general purpose register. Okay, what you have from R0 to R15, they are all called general purpose register. So this is basically, this instruction helps you in exchanging that information. Now only for MSR there is one more option available. That means when you are copying, okay, a register content into status you can do, or one immediate constant, an 8-bit immediate constant can also be copied into a status register. Okay, so these two formats are only meant for MSR. That is not true with MRS. Okay, this is only if either register to status register could come from register to status register, or it could come from immediate constant to a status register. Though the instruction is called MSR, the value may come from immediate constant based on the usage of the instruction. Okay. Okay, good. So let us see, when it is necessary to save or modify the contents of either CPSR or a SPSR of the current mode, those contents need to be first transferred to a general purpose register. Okay. After that you can decide to either operate on that or you could save into a memory. The selected bits, okay, modified, and then you can write back the value into the status register. Suppose you are interested in changing the particular bit positions in the CPSR. You cannot do some AND CPSR. Okay, you can't use CPSR as one of the operands in your register. You might have noticed in any of the register, any of the instruction format, there are 4 bits reserved for R0, RD, okay, RN, RM. 4 bits are only used. With 4 bits in the instruction, how many registers you can represent? From R0 to R15 only you can represent. So where is the space in this 4 bit to indicate that I am interested in doing a CPSR transfer? So you can't use CPSR in any of the data processing instruction. Please remember. So that is the reason why they have a separate instruction to mention the CPSR, so that you transfer that into one of the general purpose register, and then you can use any of the general purpose data processing instructions to operate on the content, and then write back that value into again the status register. Okay, good. So MRS and MSR is for exchanging the status register with the general purpose. Okay, let us see. What do? You have the saving is done by using an MRS followed by a store. What I mean to say, suppose you are interested in saving the content of this CPSR into memory. Okay, you can't do it using a data transfer instruction for the same condition that I mentioned to you. Okay, so CPR should be brought into one of the registers, and then that should be brought into memory. So you should do a MRS. Why MRS? Because status to register. MRS and then the store. Similarly, if you want to restore some value which is stored in memory into CPSR, what do? You bring into a general purpose register and then take it to CPSR. So it is a 2-step process. Similarly, when you are saving, you bring it to general purpose register, and then that general purpose register you put it in memory. This is memory, this is our CPSR, yes, this is our general registers. Understood? Very good. So, sorry. Okay. So it cannot be directly saved into memory or access. Now, all of you must be familiar with this by now. So, if you recall, the CPSR register is split into 4 fields, 8 bits each. They are called flag spot. This is called as flag. This part is called status, and this is extension, and this is control. As far as ARM7 TDMA is concerned, this is unused and this is reserved also. Please remember, the grade portion is reserved. That means we are not supposed to write anything into this. If you do so, you are doing it at a risk of preventing your program made to run on future processors. Okay, the future processors may, and it's not may, it is already future processors have used lots of bit positions in this location, and in ARM7 DMA, if you try to do something into this location, as far as you are running your code in this processor, there is no issue because there is absolutely nothing is important is there. But if suppose I am compiling the same, assembling your same code for ARM9 or ARM10 or ARM11, they are code compatible, so it may get assembled properly, your assembly written. But if you are writing something into that, it may be reserved for some particular purpose in those processors, and you may have a problem. So actually, you are supposed to take care that you don't use the reserved location of any registers always. It is a it's not true with only this particular place always. Okay, please pay attention to that. It will, you have to be cautious about that. So now you know this bit position. This is the mode, whether which mode, user mode, system mode, or supervisor mode. This is thumb mode, which we will cover later, and this is the, if it is set, it means that their interrupts are disabled. So this is the condition flag, which you are all familiar. So if you want to access any of this part of this 8-bit, you can do it using these kinds of special constants, okay, strings, special strings. So what does it mean? C means control field, which correspond to this lower 8 bits of the CPSR, or SPSR. Whatever I say is true for CPSR and SPSR, because basically this particular content only is stored in the SPSR, right, when you are doing a mode change. So those saved processor status register also can be operated upon using these commands. So the MSR and MRS instructions, you can mention these 8-bit values like this. So why they have done this kind of 8-bit value? It is again the same reason that I have told you for constants. The 32-bit instruction, if you want to save some 32-bit value, you need another 32-bit of constant to be mentioned, which is not possible with one single instruction which is of 32-bit wide. So if you recall, I mentioned that you can mention an 8-bit constant along with the MSR or MSR or MRS. So this 8-bit constant can only maximum change the value of a 8-bit value in the CPSR or SPSR. So that is the reason you are given an option to choose one of these fields to write it from a register, or it could be from an immediate constant. Okay, this is true with immediate constant also. So you could use any of them to change the particular field of a status register. Understood? Very good. So MSR is used to transfer contents of general purpose register to various fields in the CPSR, which is the same statement I am telling. But you can access these individual fields using these strings, which are these strings are understood by the assembler. Please remember, it could be a small word or a capital letter, no problem, but it should be followed by a underscore and a letter, one of this. Okay. Now this format could be with the immediate constant, or you can mention a register, and this is the format of this instruction where field mask is derived from what you have given as a CPSR fields. Okay. So I am not going to the detail of how the processor is maintaining it, but only remember that based on the field you have chosen, the processor understands which are the particular fields you are interested in modifying the value. Okay, what I mean by that, let me explain you. Assume that you are using MSR. What does it mean? You are changing the, you are loading the particular register value into a status register. Okay, so a register may have a 32-bit value, correct? May, it's not may, it is actually. So the register is having a 32-bit value, which is RM. So it is split into 4 8-bits, and your CPSR also has 4 fields I mentioned. What are they? This is conditional field. Okay, this is flags. Okay, this is control C, extension, and what are the other fields? Okay, the 4 fields which are there in this, you can mention any of the fields in your instruction. So You could even combine those fields into one instruction. Okay, I will explain that in the subsequent with an example. So you can change any one of them. You can choose, I am interested in changing this and this, or I am interested in changing only this and this. So based on that, you can decide to put one of these fields, C, X, or S, or F. Okay, so you can say CPSR. Okay, and then say I am interested in C and X. Okay, that means it will only modify the C is control fields. So this field it will change, and then if you mention X also underscore CX, that means it will change the extension bit also. That means given a register, it will choose those particular 8-bit value and then copy it into the status register. Okay, so you can in fact say that I am interested in changing all of them. That is also allowed. So that's why they have provided, but only okay, you can mention a unique value in those registers and then transfer it. But please remember, in ARM7 TDMA you are not allowed to change these contents. These status and extension fields are not used in the 7 TDMA processor. Okay, so I hope this is clear to you. Let us see and take an example so that you understand exactly how it happens. So should only write those fields that I can potentially change. Okay, again you please remember, some of the mode registers are not modifiable by a particular mode. So in a user mode you cannot change the mode register, mode field of the register. That is to be precise, I will go back. Please remember, this mode bit cannot be modified in the user mode. You can change these bits, and even this thumb mode you cannot change it using this instruction. So you have to make sure that whenever you are changing the bits, only those bits are modified in the values and put in R0, and then you are storing them into CPSR. Otherwise you are likely to get unexpected results. Okay, that is what I am trying to say here. Let us see one small example. I prefer you take a break now and then try to look at these instructions and then come back and see what the explanation, whether you are able to make sense out of this. Okay. So welcome back. So I hope you already understood what is happening here. These instructions are all executed one after the other. What happens here? We are loading the CPSR into R0. Please remember, when you are using the MRS instruction to access the CPSR, you are not mentioning the field. It is only when you are writing into them. So here you can say I am interested in reading a CPSR or SPSR based on which mode you are running this instruction from, and it will copy that value into one of the general purpose registers you mentioned here. It now CPSR value has come here. What are you trying to do here? Not you, I am trying to do. I'm sorry. So what I am doing? I am trying to AND the value in the lower LS byte. Okay. So I am interested in only the lower byte. So FF I am doing, ANDing it with that. That means all the values which I read from R0 is maintained here. All this value, whatever was earlier there in copied from CPSR, is made 0 now. So R0 is holding that value now. Okay. Now I am using an R1 here and then trying to do a MEN with the 1F. By now you are familiar with the MEN. What happens? Whatever is given here is inverted and then copied into R1. That means the lower 5 bits 1F. Okay, lower 5 bits are set to 1, or rest of it is all 0. Okay, so only lower 5 bits, that means which corresponds to the mode bits of the CPSR. Now what are you trying to do here? Means I am trying to AND R0 with R1. Okay, and then getting it here into R0. So effectively I am extracting only the 1F portion. Okay, because 1F what has happened is 1F is 0, and then if you AND it with the rest of it is 1, so the rest of it is preserved, only this is forced to 0. So what you see in R0 will be, okay, earlier you had this content which you read from this. Assume that suppose you have read this value. Okay, these 8 bits were preserved, suppose. Okay, these 8 bits were read from CPSR, and after this operation, this is what you are having it in R0. Now I am doing a ANDing it with all ones here, and then only this 5 bits I am ANDing it with the zeros. Okay, so what I am exactly doing is I am making sure that the top whatever 5 bits were there, whatever was the previous content, I am making them all 0, and then I am preserving these values. So this happens to be 001, and then top 5 bits are made all zeros. Okay, this is what is the RF content, R0 content. Now after that I am ORing it with 13. That means I am interested in 13 is what? 1 0 0 1 1. So this 5 bit 13 is corresponding to this value which I am ORing it with. That means now I am changing the value for only these 5 bits, keeping this content same. Okay, now I have got a new content for the lower byte, which the top 3 bits are the same. Okay, what was there originally, and then these bottom 5 bits have been modified to represent a maybe another mode, and then which happens to be a supervisor mode, and then I am writing R0. See here, C I am mentioning here, CPSR C. That means I am interested in only modifying the lower byte of the CPSR, and I am using MSR. So now what happens is the mode is changed from originally whatever was the mode. Assume that you are in a privileged mode so that you are able to change the mode bit. It will go back to the supervisor mode now because I am changing the value to 13. Understood? What I am trying to do is I am getting the value into R0, making sure only I am interested in top byte, and then in that I am only changing the lower 5 bits with the new content and then writing it back. I am making sure that the top 3 bits of the lower byte are not modified. Suppose interrupt flag or thumb mode or whatever was the status, I am maintaining the same thing and getting it back. Okay, writing into the CPSR. This is what is done by this particular code, and I want you to write such a code to become familiar with this. Okay, so what are the usages? As a part of the read, modify, write, read it, modify it, and write back. PSR is, it could be a CPSR or a SPSR. So one more thing you should remember, in this little bit I will explain you later. When you are changing the exception mode, it could land it into multiple exceptions happening from the same. Okay, one exception calling the same exception again come inside. So in those kind of situation, you may have to save it into stack. Okay, I don't want to go into the detail now because it is out of context. Let us talk about that when exception happen. Right now, take it from me that when nested exceptions happen, you need to save the value in SPSR into stack and then restore back. For that also, you will be using the MRS and MSR instructions. Okay, and even to save process states, context which I mentioned, even for that operation, you will be doing this. Okay, with this, we are coming to the end of that. Okay, in the immediate form of MSR can be used to modify the PSR, but make sure that you don't disturb the previous content or other contents. And if you are modifying all the bits which are part of as yet unallocated, you are likely to get into trouble. So don't do that. Don't modify with the bits which are not supposed to be touched by you. Failure to observe this rule, you will get an unanticipated side effects when you are moving to future versions of ARM. When I say future versions, means if your code is compiled or assembled, in this case assembled for a future versions, you may land into trouble. The program will not work properly. So portability will be an issue if you don't take care of this. And then other restrictions, you have to modify. One small thing I just thought I will make a note of that. The flag register, if you recall, the only top 4 bits are having CZNB, right? The top nibble of lower byte is all unused, reserved. Even though they are reserved, you will be allowed to change them by using this instruction. Okay, you are mentioning a 8-bit value, though you are modifying only the bottom nibble. Okay, in this case, CPSR bottom 4 nibbles are CZNB. Okay, so you are interested in only changing them, but when you mention F, the F field will indicate all the 8 bits, right? So you are allowed to change this contents also, though it is part of the reserved field. Okay, that they have given freedom, because you cannot transfer, minimum you can transfer is 8 bits, right? So how will you make sure that you don't change this? There is no guarantee, no, you cannot do that. So they have given a freedom to you that you modify. Will make sure that it doesn't impact the future versions of the ARM. Okay, that I thought I will make a note of it, so you remember this. Okay, you may have this question later. So ARM will take care of not to get disturbed when you write something into this. Okay. Other than that, no other reserved value should be changed. And the mode also you can change only when you are allowed to change. At the same time, you also have to give only the reserved value. If you are using undefined values, okay, more bits, you can remember the 5-bit values are fixed. You cannot write any other numbers that you wish. If you use some reserved value, you will have a problem. Okay. And one more thing, if you recall, there is no S bit option here, because we are doing something with MSR and MR, which is CPSR and SPSR. There is no S bit, or you cannot say MR of S. Okay, there is no special word, the S, you cannot mention it here. Okay. Additional information, you have to do any operation with SPSR only when that mode, particular mode supports it. Okay, you cannot do it in user mode or a system mode which doesn't have a SPSR register. Similarly, only privileged modes you can modify the SPSR. You can't do that with the user mode. Okay, and SPSR register which is accessed depends on the mode at the time of execution. Suppose you are in a fast interrupt and you are accessing SPSR, it will access the particular bank of that particular exception. Okay. So you don't have to mention that underscore FIQ when you are writing the code. You will be writing SPSR, but based on the mode in which that code is executed, it will access the relevant bank register which is active at that moment. Similarly, a very important point, this thumb mode I will be explaining you later in the section, but you cannot modify the thumb bit using this MRF MSR instruction. So please remember that you preserve those values, because you may not know whether it is already in thumb mode or not. So you should not change this bit. Okay. And one more condition is R15 cannot be used with this instruction. Okay. So I want you to spend some time on this and then understand how this instruction execute. You can take a small break, 2 minutes break, and then try to see how these instructions run. Assume that ARM is in a system mode. Okay, what I mean by system mode is you are allowed to modify the mode bits. Okay, because in the user mode you cannot allow. That's why I'm saying that ARM is in system mode. And then if these instructions are executed, what happens? You can take a break now. Okay, welcome back. Let me run through that. By now you should be familiar with this. If you are done yes here and then you are moving a 0 here, it could have been set and it will be true. Okay, it will execute this instruction. So CPSR comes into R1. Here you are moving a 1, so this won't be true. So this will not happen. And here, what are you trying to do? You are trying to write the conditional flags with all values. So you can forcibly write all ones into CZNV. So you can do that. Okay. And one more thing, what you are doing here is, I am not mentioning only the condition flag here. I am mentioning the, please remember, I am mentioning F. Okay, let me re-exam. I will write so that you recall. This is condition spot. This is the flag spot of the CPSR. So I am trying to modify this as well as this with a byte value. Okay. So what happens is this D0 gets written into this, and then all zeros will be written into this, because this D0 will be 0 extended, and then it will, this constant is read as a 32-bit value, and then it uses the lower byte value to copy into C bit. Though you have mentioned CF or FC, doesn't matter, because you are interested in changing these two flags, these two fields of the CPSR. So it does modify whichever, this is the lower byte, so it changes the mode bit first, and then it fills only the top CZNV flags. Four flags are meant are set clear to 0. Okay, that is what happens with this instruction. Okay, I want you to spend some time on this. What this D0 means. This is 1000 correspond to which mode? We are changing the mode. Okay, user mode. Okay, this corresponds to user mode. If condition field as well as mode fields need to be changed together, then you can do this. Okay, very good. So I am done with the flags. So I thought as a continuity we'll take some more time to finish up this set of instructions also. So we'll let us carry forward. I have taken a little more time than expected. Okay, move loading constants. You remember we could load some constant value into some register. I told you that 32-bit value cannot be moved because of the instruction restriction. So, but you could use move or MVN for this. If you are mentioning any constant, if you recall, I mentioned some instructions are there where the constant value can be rotated by some bits, and then that can be reserved values can be used. So processor does, the assembler does some choosing a particular register, instructions to based on the value that you are mentioning, which constant value you are trying to copy, it picks up the right instruction to do that. Okay, because of the restriction that ARM instructions are 32-bit in size, you cannot mention a 32-bit constant, but it chooses a particular type of instruction to do the job. Or it could also do one more thing, it can save the 32-bit constant in the memory. Okay, 32-bit value, if you are interested in copying, suppose you are interested in copying 0x12345, then if you say move, it cannot be mentioned as a move, so it will reserve some location in the memory and put that value there, and then do a load register. Load LDR means it will copy from this memory location to the register. So it can do a memory transfer to perform the same job. Okay, so I am trying to explain you what are the things that the processor supports. So there are two instructions which are called pseudo instructions. Okay, what I mean by pseudo is these instructions are not executed as is by the processor. It is understood by the assembler, and then it will modify this instruction. It will only know the intent of the programmer, and then it will modify it to suit a particular thing that you are interested in doing. Okay, I will explain you what I mean by intent to do. Only thing is these instructions are modified by the assembler to perform the job. So effectively you are communicating to the assembler that I am interested in doing this, and the assembler generates multiple instruction or single instruction internally to achieve the job. Okay, so let us see. LDR is to load a particular 32-bit constant, and load address means you are interested in loading a particular label. The label could be a part of an instruction where you are interested in loading the, suppose there is a code. Okay, there is a label you have mentioned in your assembly code. That means it is referring to the particular part of the code. So this code can be anywhere in your code memory, and then you are interested in getting the address where the code is there. So you may say that I am interested in getting that address of the label into this register. Then the processor will do something to do with the PC. Maybe it will perform some operation with respect to PC to get this value, or it could save this constant somewhere and then load that into the register directly. Okay, it can perform any of those operations based on the particular usage and where you are calling that instruction from. Okay, it is aiding in programming. So the first pseudo instruction writes the 32-bit constant to a register with whatever instructions are available. So it can use any instructions to achieve a job. It could be a PC relative, it could do with respect to the PC, or it can do a memory read operation. One example I will show you. Suppose you are declared, you are trying to say that I am interested in copying. You have declared two values 1, 2, 3, 4, 5, 6 and this in your code, and then you are saying that I want this constant to be loaded into R0. From this you can make out that 32-bit value cannot be given in this instruction. So what exactly the processor does? It actually changes to a load register into R3 with respect to PC. So it generates some offset with respect to the current PC and then tries to access this constant which is there in the memory. Assume that this code is given in the assembly code in the same sequence it is as it is mentioned here. This is these two are two instructions. Okay, assume this is at the location 1000 again, 100. Okay, for a change. 104 this instruction is there, 108 this instruction SWA is there, and 100C 10C this word is stored. Please remember, code and data, they can reside in the same memory because we are one Harmon architecture we are having, and this code and data memory can be same. They can be together. Only thing you have to make sure that you don't give R15 the PC to point to the data area which you have reserved. So 10C and then this will be 110. Okay. Now the processor, when it is the assembler, when it looks at this instruction, it is generating a particular instruction with respect to PC. It is computing the offset. So you may remember I have mentioned that instructions which refer with respect to PC. Okay, LDR instructions where you can mention R15 as one of the operands. So you have to now think, okay, where the PC will be when this instruction is executed. Bring in the pipeline into your mind where the PC will be pointing at, and then how much of offset it should mention with respect to PC to access this value which is there in the memory to be brought into R0. Okay, I want you to just think it over rather than me telling everything. So here offset of the PC, offset with respect to PC is computed, and that constant, this is going to be constant because when the assembler is assembling this particular set of instructions, it knows that these instructions are one after the other. So it will be placed together in the memory. So it can always compute the offset with respect to PC where these constants are residing in the memory, and then it will be copying that into R0. Please remember, this dot word is a notation used for loading this particular constant in that particular address. After this SWI, this is stored in the memory. Okay, if you look at the memory, if I show the code memory, you will see the instruction for LDR R0 here, and then R1 LDR is there, and SWA is there, and these constants are stored in this location. Okay, in the memory. Just for the clarity I am saying, and all of them are 32-bit wide. So the memory. So if this is 100, you can know that where these constants are residing in the memory, and then with respect to PC, can you compute the offset? Okay. So what is the offset value? Okay, you can even take a small break and then find out what is this offset is going to be. Okay, welcome back. If you have thought over and if you remember the pipeline, if when you are executing this instruction, where the PC will be, PC would have accessed already this instruction, and then it would have accessed this also. So it will be actually wherever this instruction is, okay, plus 8 will be the PC value. Okay, when this instruction is getting executed, please remember the pipeline again. Okay, 3 stages. When it is in execute stage, this particular instruction, already PC has fetched the instruction 2 down the line. That means the address would be 108. So any offset that is then performed with respect to PC should accommodate or account for this particular change in the PC value. So it is just from this location, it is just plus 4, isn't it? This particular word is stored. So the offset here will be 4. Plus 4 or minus 4, it is a plus 4 because it is in the increasing order. So wherever PC is, plus 4 is what this address is stored. Now tell me what is the offset for this instruction. Once the PC moves here, okay, when it is executing this instruction, this PC also would have moved 1 ahead, right? Please remember, it is accessing this memory, but it won't be executed. Okay, now PC will be pointing at this location. Okay, and again this word will be plus 4 from there. So here also the offset will be 4. But why I have put this word just below this SWI? Because SWI makes sure that the control goes back to the simulator. This is very specific to our ARM simulator that we are using for our course. So there is no harm in declaring some data elements here. So you won't have any problem. Okay. So 4 will be the answer. Okay. Remember that code and data can reside together because of one-node architecture. Okay. So ADR example, ADR is it is copying the address of the variable. I am declaring a num1 using this particular simulator. Various simulators or assembler may have different conventions, so you have to remember that accordingly. Suppose if you are interested in doing this, what exactly this ADR instruction does is it stores the address of the variable where it is declared. Please remember, it is not accessing the content of the variable. It is declared here. Whatever is the address here, that is getting stored into R2. Whatever is the address of num2, it is stored into R3. Again, this will be with respect to PC again because it is coming one after the other. So the assembler, when it looks at this particular instruction, it actually generates some PC relative accessing. In fact, it will generate an add instruction to say that whatever the PC value here, add 4 and then get that value into R2. Okay. So that is what it does. Why? Because these addresses are in the PC, related to PC. PC is the program counter I am referring to. So this instruction has an access to PC at this moment. So it can compute the address, that 2-bit address with respect to PC and then comfortably load into R2. Okay. So to get the address of a variable, the assembler might change the pseudo instruction as address load with the PC relative instruction. So I want you to try this out exactly the same way in our simulator, that sim SHA simulator, and decode the code and then understand what exactly the instruction being generated. Okay, that will give you a better clarity. So I hope all of this is very clear to you. I want you to try out all these things in your lab session to understand the concepts. Okay. So there are pseudo instruction. It will check if the given constant can be represented by an operand 2 immediately. Otherwise, it will use different instructions. So move instruction will be faster. See, assembler is deciding what to do. So it could do a move instruction or add instruction rather than doing a LDR instruction. So based on the constant that you have mentioned as a part of the LDR or ADR instruction, the assembler is free to choose whatever instruction it wants to perform the job. So that is what is mentioned here. Okay. So some of these constants are 12-bit constants which can be represented using the instruction that I mentioned in the session 7. Okay. If you don't remember, please go back to that and read that material and to understand how this instruction can be executed. So with this we have come to the end of the session. So I hope you are clear with both these instructions and all the different ways of using them, and only when you try this out in your simulator and understand it, you won't have the hang of this. Please do so, and happy to talk to you. Wish you all the very best. Take care.